In this episode, we will focus on the synthesis and analysis of momentum conservation in special relativity. Studying the conservation of momentum in the collision of two spheres in a relative frame provides deep insights into the behavior of objects moving at high speeds. The scenario constructed in the video exemplifies the conservation of momentum and energy. In a central collision, the total momentum before and after the collision must remain constant. Given the symmetry, the perpendicular components of the velocities are conserved, leading to the observed post-collision velocities. Assuming an elastic collision, kinetic energy is conserved. The kinetic energy before and after the collision in each frame can be calculated and verified to be equal, thus establishing the conservation laws. This thought experiment elegantly demonstrates the basic principles of Galilean relativity. The velocities perpendicular to the relative motion of the reference frames are not affected by the relative motion itself. This invariance is very important in classical mechanics and sets the stage for understanding more complex relativistic transformations where velocities approach the speed of light. Furthermore, the central collision emphasizes the robustness of the conservation laws. Despite the relative motion of the frames, the basic principles of conservation of momentum and energy remain valid, providing a consistent framework for analyzing physical phenomena. Consider two observers, each in their frame of reference. Let's call these frames S1 and S2, moving relative to each other in a straight line, like two parallel trains moving at different speeds. Let's say observer 1 is in frame S1 and observer 2 is in frame S2. They observe and interact with two identical spheres, A and B. Frame S1. Observer 1 throws sphere A vertically upward with a certain speed. Frame S. 2. Observer 2 throws sphere B vertically downward with the same speed, but in the opposite direction. These spheres, A and B, are placed on a collision course because the origins of their frames, S1 and S2, will coincide at some point. This setup ensures that A and B meet at exactly the moment when their two origins coincide. At the moment when the origins of S1 and S2 coincide, spheres A and B collide head-on. This type of collision is central, meaning they hit each other directly at their centers. After the collision, sphere B, which was initially moving downward, moves upward at the same speed as sphere A before the collision. After the collision, sphere A, which was initially moving upward, moves downward at the same speed as sphere B before the collision. The scenario is a clear demonstration of Galilean relativity, which deals with how different observers moving at constant speeds relative to each other perceive the same event. Two reference frames, S1 and S2, are moving relative to each other along a straight line. However, the vertical motions of the spheres, up and down, are perpendicular to this relative motion. Since the vertical motion of the spheres is perpendicular to the relative motion of the frames, it is not affected by this. This means that each observer measures the same speed for the vertical motion of the spheres, even if the spheres are moving in opposite directions. The total momentum of the system, the combined momentum of both spheres, remains the same before and after the collision. The only change is the direction of the sphere's motion. The kinetic energy of the system is also conserved in this elastic collision. The spheres change their speed, but the overall energy remains constant. This experiment highlights the robustness of the principles of classical mechanics, even when dealing with different reference frames. The conservation of momentum and energy is clear and shows that these laws hold regardless of the relative motion of the observers. In essence, this scenario, where observers in S1 and S2 watch spheres A and B collide, provides a vivid demonstration of how relative motion and collisions are perceived in classical mechanics. It reaffirms the invariance of normal velocities in Galilean transformations and the fundamental conservation laws that govern physical interactions. This understanding is crucial for both theoretical discoveries and practical applications in physics. It addresses the conservation of momentum in the framework of special relativity by applying the principles to the collision of two spheres, A and B. This scenario assumes that the law of conservation of momentum in classical mechanics holds in the domain of special relativity. We analyze the impulses, momentum changes, of spheres A and B before and after the collision, as measured in the reference frame S1. The expression momentum is equal mass times velocity in classical mechanics is modified to include the factor gamma in relativity to ensure that momentum properly accounts for relativistic effects as speeds approach the speed of light. This means that despite the relative motion between S1 and S2, the conservation laws hold in all frames, demonstrating the consistency of physical laws across different inertial frames. This invariance forms the basis of the principle of relativity, according to which the laws of physics are the same in all inertial frames. Collision dynamics are more complex in relativistic mechanics due to their dependence on speed and the Lorentz factor. The transfer and redistribution of momentum are significantly affected by relativistic corrections, reflecting the nonlinear nature of relativistic dynamics compared to classical mechanics. This analysis is not merely theoretical, it has practical implications in high-energy physics, where particles often move at relativistic speeds. In the words of Einstein, relativity teaches us the connection between different descriptions of the same reality. The scenario described here is a demonstration of this profound insight that unites classical mechanics and relativistic physics in a seamless continuum. The expression m0 indicates the rest mass of an object, which is the mass measured when the object is at rest. When the object is moving at a speed of v, its relative mass increases according to the formula given by m times v. As the speed approaches the speed of light, the denominator approaches zero, causing m times v to approach infinity. This means that an infinite amount of energy is required to accelerate an object to the speed of light. This increase in mass with speed has been confirmed experimentally with electrons in particle accelerators. Precise measurements of the mass of electrons as they gain speed confirm the predictions of special relativity. As electrons are accelerated to high speeds, their mass increases significantly, consistent with the theoretical relationship. Theoretically, this means that no object with mass can ever reach or exceed the speed of light, because doing so would require infinite energy. This is a fundamental principle of special relativity. In practical terms, this principle is very important in the operation of particle accelerators. These devices can accelerate particles to speeds very close to the speed of light, but the energy required increases significantly as the speed increases. Understanding the relative increase in mass is important to modern physics, especially in high-energy physics and astrophysics. It affects calculations involving particles moving at relative speeds and is critical to the analysis of cosmic rays and other high-speed phenomena. The relationship between mass and velocity in special relativity reveals the profound implications of Einstein's theory for our understanding of motion and energy. The rapid increase in mass not only limits objects from reaching the speed of light, but also ensures the consistency of the laws of physics in different frames of reference. This fundamental aspect of relativity continues to be a cornerstone of both theoretical discoveries and practical applications in physics. Thanks for listening. Stay well.